So let's think about it. What is my inductance value? How do we calculate inductance? You remember? The only equation that gave you inductance and capacitance is your ripple equation, right? If you remember, what do? We have I of L, and this I of L has the slope. The slope comes from V of L. So why? Because we have L di by dt is equal to V of L. So di by dt, which is the change in current, is equal to VL over L. So when we did this delta I, we said we have two delta I's, right? These two delta I's will be equal to the slope multiplied by the interval. So you have two options. You can use the DTS interval or the D prime T of S interval. But in each one of them, you have to use the right V of L. So that's exactly what I did here. I used the D prime. So what is my V of L? Where did this V of L comes from? This V of L came from my steady state analysis that I did up here. So V of L is equal to VG minus V out minus VD on when the MOSFET is up. So I use this V of L, and here it is, and I divided it by L to give me my delta IL, which is the change in the current. So going back here, so I have L is equal to V of L in that interval divided by 2 delta L. Why 2 delta L? Because the average value is here. We have one up, one down. But this V of L is the whole slope, right? So it's the whole line, which is 2 delta L. So 2 delta L is equal to VL over L times the interval that's in, and for my case, I chose D prime T of S. You are welcome to use any of them. Both of them are going to be correct. If you're going to use the D T of S, you need to use the other V of L. So the other V of L here is VG minus IL R on. So you need to use that if you're going to use the interval of the DTS. Okay? So now, what's my concern? What do I know? I can find my I of L. How did we calculate the I of L for all cases here? You calculated I of L for all cases by your capacitor charge equation that we drove in here. When we put the I of C average to be equal to 0, then I was able to calculate my I of L. So this is the steady state I of L, which I need now for my inductor value. Why do we need it? Why do we need it? Let's look at this equation. What do we have? VG, I know what it is. V out, I know what it is. VD on, I know what it is. Duty cycle, I calculated for. T of S is also given because it's 1 over F of S. So what do I need to find? I need to find my inductor ripple. So how do I find my inductor ripple? Your ripple has to be a percentage from your I of L. But I have 4 cases, so I have 4 I of L. So based on which one should I choose? Based on which one should I choose? I go back to the point that I had in here. You go here and it tells you again. The converter should operate in continuous conduction mode, and the ripple specifications must be met under all operating conditions. So it means what? It means that the ripple I choose have to be meeting all of those cases and make sure that I'm still running in continuous conduction mode. What does continuous conduction mode means? Do you remember from chapter 5? It means that my minimum delta IL, or the ripple, will be equal to I of L. If delta I of L is greater than I of L, then it will go negative, right? It will go down. So it means that I'm going to go to DCM, discontinuous conduction mode. So if I want to make sure the converter operates in CCM, then I need to choose the smallest I of L here and choose my ripple to be less than that. So again, it tells you what? The ripple was chosen in this case to be 0.8. You can choose any number you want because it doesn't really give you a certain number. But it has to be smaller than the smallest current out of those 4 cases so that you can guarantee that you stay in continuous conduction mode. Okay? So usually in the book, it tells you choose the ripple to be about 10 to 15%. Yes, that's correct. But since we are doing it for all the operations, I need to make sure that it is smaller than all the currents, smaller than the smallest current. And that basically guarantees that I stay in CCM, and that's what the project requires me to do. So in this case, it became actually resulted when we chose this 0.8, it resulted to be 6% of your maximum current because your maximum current is 12.6. which is okay. I mean, which is okay. It might be less than usually what they use 10%, but it is okay because you are guaranteeing that you are in that value. Once I have delta IL, then I basically have everything that I need in this equation of the inductance. So I solve for it. How many values will I have? I will have 4 values. Why do you have 4 values? Because the equation depends on VG, so this VG will have 2 values that it changes, but it also depends on D prime. So I have 4 D primes, I have 4 cases for the duty cycle. So I have to stay with the 4 cases. So I calculated 4 inductance values, like you see in here, this L's, and they are all pretty much close to each other. They don't have to be close. We'll see in the capacitance, they will not be close. But in this case, they came up to be close. But then what? Am I going to be changing the inductance every time I'm running my simulation? No. Why? Because in the hardware, you're not going to build a converter with 4 inductances and it's a plug and play. It's 1 inductance has to fit all. So what can I do when I say worst case or the best, or what should be the best? The best would be always the largest. Yes, largest is not what you want, but largest guarantee that you can work in all conditions. So my largest here is going to be 37.7. So what can I do? I needed to round it because I was asked to round my inductances to 2 significant digits. So if we go down in the problem here, it will tell you here. This is the capacitance. We should have one line for the inductors. Here, it says, in your design, you're allowed to use inductor values with 2 significant digits and standard 10% capacitor values. And I'll explain the capacitor part next, but for the inductance, we basically are gonna round to 37.7. It's basically 38 or up. I just chose 40 microhenries for my case in here. So this is answering our inductance. Any questions? Any questions? Okay, are you guys all following? Okay, so the capacitor value, what is the capacitor value now? Again, it's the exact same equation, but it is on the voltage. Why? Because C dV by dt is equal to I of C, right? So the current I of C divided by C will give me my change in the capacitor voltage. So this delta V is basically, delta V is what? Delta V is your I of C over C. So I of C, we got it already from the equations for the capacitor charge balance. So now I can do the exact same thing. I can choose either DTS or D prime T of S, and that becomes your I of C divided by C is equal to 2 delta V out, and delta V out is given to you. We actually were given that delta V out have to be less than or equal to 50 millivolts. So I just chose the maximum, which is 50 millivolts, and calculated based on this. So again, what are we gonna have? We're gonna have 4 values for the capacitance. Why? Because we have the power, which is changing, we have the duty cycle, which is changing. And again, the duty cycle that you choose needs to match the case that you have. So the power output will have to match those cases. And once you calculate that, you will see that we find 4 values for your capacitance, and they are ranging pretty much. So this is like 14, 153, 12, and 124. So once we have those 4 numbers, then what are we going to do? We need to choose a capacitance. So the capacitance here, the largest one is 153. But what am I asking? I'm asking for standard values. So again, if you just went on Google and said where's the problem, sorry. So if you went on Google and you said 10% capacitor values, standard 10% capacitor values, it will give you values for it. And those values, you need to choose the next higher from this 153. So in this case, I actually went with a little bit higher, and we went with 330 microfarads. And let's remember, there is no one right answer, one wrong answer. As long as your procedure is correct and you're justifying why are we taking your assumptions and your choices, then you are covered. Okay? So this is the capacitor, and then the ESR of the capacitor, R of C. R of C, if you remember, sorry, let's go here. R of C is given to you as 1 microsecond over C. So that's how you find its value. And if you remember, when we talked about the project, I told you don't consider it when you're doing the equations so that it doesn't complicate the equations. And that's what we did now. So we didn't consider this one except after we found the capacitor, using this equation that was given to us here, we calculated our RC value, and then we're going to use it in our simulation. So let's go back in here. So I'm just showing the duty cycles, what they are given for different cases. So that's a table to summarize what you have found from each one. And then this is just a verification that for each case, when you calculate for it, it will give you the delta I of L and delta VO within the range that you need. You don't need this step, and this was not like penalized for anything. It's just an extra step to verify that my design was those choices of L's and C's meet all 4 cases on the ripple side. Okay, with that done, then we go back to our problem here. And what do we have? We finished the duty cycle, we finished the inductance, we finished the capacitance. Now what do we need to calculate for? We need to calculate for the currents and voltages. All what you're asked to do is you're asked to calculate the ones for the diode and for the switch. And let me show you how we can calculate this. So after calculating the values of your L's and C's, we should find the values for those MOSFETs and diodes. Why are we doing this? I mean, so it's not like everything that was written in the project for you to calculate for was there for a reason. It was not just there to give you more values and try to do more stuff. What are we designing for? We are designing for the converter. What are your components? L, C, diode, MOSFET. So we're done with this L and C, duty cycle, and then now we need to choose what MOSFET and what diode we need to use. And that's why to choose a MOSFET and a diode, you need to know what is the current that's going to flow into it and what's the voltage that's going to flow into it. And that's why they are actually written to you in this way. Okay, so what is the peak current? What is the peak current? It's always I of L plus delta I of L. Why? Let's go here. This is how we plot our current. So this is your average DC I of L plus your delta I of L to give you the peak point. So it is IL plus 1 delta IL will give me my peak value. Right? So this is the equation that we're using here. I of L will be IL plus delta IL. Again, worst case scenario, I'm not doing anything except I'm plugging it for the 4 cases. So I'm calculating it for the different V of G and P out, and I calculate an I of L for each one of them. Once I calculate all of the 4, I choose the biggest number and say this is the worst case I have here. So again, this worst case, I felt it was scaring some of you, but I don't understand why. You're just getting the equation, you're calculating it for the 4 cases, and then you're choosing the biggest one as your worst case. Why? Because you need to choose a device that can handle the maximum current, maximum voltage that's going to go through it. So this is basically your worst case scenario. Okay? So then, after that, what do you have here? We asked for the diode peak voltage. So where's VD? How do we get VD? So let's go here to the schematic and think about your voltage across the diode. So what do we have? So the equation here tells us VD will be equal to the drop on this MOSFET and V out minus V out. How do we get this? Just a KVL equation. So in this KVL equation here, you basically have the voltage across the MOSFET, which is basically just your R on times I. You have the voltage across the diode, and then you have the output voltage. So this is this KVL on this loop. Okay? So that basically defines what your diode voltage will be. So I get my diode voltage. Again, my maximum diode voltage will have the inductance, the voltage V out. So V out is the average value plus the delta VO. IL will be the same thing, will be the value plus the ripple of it. So those ones you have to consider here. Again, if you didn't put those ripples, we did not take off points. So it's basically just the average value, just to make sure that you understand the equation and how you're choosing it. Again, we have to do it for the 4 cases. So you do it for the 4 cases. Why 4 cases? Because your I of L depends on your power, so it will change. Once you calculate it for those 4 cases, you choose the worst case, which is the largest voltage. Then from this one, you actually calculate your current I of D, which is the diode current. and this diode current, I of D is equal to I of L times D prime. So where is that coming from? Again, let's go to our circuit. So where is the schematic? This is I of D, right? So I of D, if this one is open, then it is going to be equal to I of L. So it's only I of L when you are running the diode part, which is the D prime part. So that's here. Sorry for the noise. So the I of L will be equal to whatever the equation that you got in equation up in here in equation 7, and then this is basically your I out, which is coming from here.
This one, Dave.
So
Very nice.
okay, so let's go back. Sorry, I'm just gonna go down. Okay, so now let's go here. So we got the voltage across the diode, the current across the diode, and we again calculated for the 4 cases of your I of L. So you have your I out, 4 cases, and then the power output for the diodes is PD is equal to I of D times the voltage. So again, you have 2 equations for the power because I saw inventions of different equations for the power. So you have either P is equal to V times I, or you have P is equal to I squared R. So again, the power is equal to V times I here because we calculated the voltage across the diode and the current across the diode. So you multiply them together and you get your loss, which is, for this case, was about 3.65 for the diode. Then after that, we want to do the same thing for the MOSFET. So what is the MOSFET now? The MOSFET is the opposite of the diode, right? So if I'm using the same KVL equation that I have in here, so when the MOSFET is not working, then the voltage of this part will be what? The on of your diode plus your output voltage in here. So that basically defines your MOSFET voltage. So this is V out plus VD on. And then again, you calculate for it. And for this case, since we only have the V out, then you have only one case because you don't have the power or the input voltage related into this one. And that's how it calculates. For the RMS of the current, I actually don't, I know that you could not drive this equation. So this is not what we are asking you to do. All what I'm asking you to do is if you have this I of L and then you divided it by square root of 2. So it's basically, again, I of L times D in this case, because the MOSFET is turned on. So it is when it's the same current, I of L times D. And then if you divide that by square root of 2 just to get the RMS, then I think you're covered by this.
Yeah.
Again, anything that was closer to that one, you got the points for it. If anything that doesn't show that, let me know. You calculated for the current for the 4 cases. And then now I have my voltage and my current, so I can calculate my power loss. And for this case, I'm using the other equation because I have the R on. So I have I squared R on to give me the power across the MOSFET. And this is your worst case scenario. With that, then this solves everything that you were asked to do. And then we have the efficiency. This is the last one. So let's go to the list again. So we calculated the steady state, inductor values, all the values for the worst case scenarios. And then the last thing that you were asked for was to estimate the DC efficiency. And for this case, it's defined for you what you want to do it at VG nom and V out max. So this is your nominal condition. It's VG nom and V out max, right? So what is the efficiency? It's your output power over your input power. So it's whatever things that you lost in between divided by the full power that you started with. In this equation, I'm actually plugging in for what is the input power. So output power is given to you. So let's go back in here. Your output power is given to you because you have this 25 to 250. But what would be your input power? Your input power is VG times IG. And IG is equal to I of L. So that's basically what I use for my efficiency equation. So P out, I put my P out, and then I divided that by VG times I of L. And then from this one, you can actually simplify it. So in the end, you end up with about 93.8. Again, this number might be a bit different, but it should be the same if you're using those nominal values, because it depends on the duty cycle, which all should have the same value for the duty cycle. It depends on the output and input voltage. So you should get the same efficiency on here.
Yeah.
Let me stop for a second in here and get your questions, and after that we're gonna go to the next step. By that we actually did all the calculations that's in here. Any questions? Is it clear?
See how it does that? I don't get that. Look at the screen.
Can you just say yes or no? I mean, I need to hear that it's better for us.
Yes, ma'am. Yeah, it's pretty clear. Thank you.
Okay, perfect. So let's keep going.
Seems like it's always the same.
So with that, then we actually have all the calculations, and then we're done with here. So what did it tell us after that? It told us that we need to choose from the list that was given to you on Blackboard. You need to choose a MOSFET and a diode that will fit your design. So how do we choose a MOSFET and a diode? We basically need to look at this current and voltage that I'm still sharing, right? You guys can still see my screen?
Yes.
Okay.
Yes.
Okay, thank you. So this is my current and voltage that I calculated for the MOSFET and diode, and based on those values, you go to the list and choose it. So for example, for me, for the diodes, I chose the 100 and the 7. Why? Because you need at least 1.5 times your current and about 2 times your voltage, and that's what I mentioned in class before. So I'm gonna choose 100, so that's 48, so that's basically double the voltage. And the current is calculated as 5 amperes, so this is basically 7, so it covers. There was other cases which have like 10 or 20, you can choose that. You don't want to overkill, which means I don't want to choose 1,000 volts. I want to choose something that's in between or close to 2 times the voltage and 1.5 times the current. The same thing with the MOSFET. So I chose the values that I calculated as my worst case scenario. And then based on those 3 values, I went and I chose something. So what are the 2 columns you're looking at? You're looking at your voltage column and you're looking at your current column. And we said only worry about your 25 degrees centigrade because it's giving you the 100. Because if you remember, somebody asked in class and we said, worry about this 25 degrees. So it's basically 1.5 times the current. Okay, so this you selected. Usually in older projects, I told them that they have to simulate it 2 times. Simulated 1 time with the simple switch models and then 1 time with the detailed ones. However, for your case, we actually took that out of the project. So we're only doing it for 1 case, which is the simple one. So up till this point, now we're done. This is telling the part that we already used, which is the inductor to 2 significant digits and the capacitor value. So we're done with all of this. Now we go to the last part of the project, which is verifying your transient analysis. And we were given 2 options, either to use it in PSpice or in MATLAB. MATLAB is very similar to what we did in class. I know that some of you write comments in the project that it was very hard to set up the MATLAB and you didn't know how. So I would like to take this separately because again, we're gonna do another MATLAB session for project number 2 and try to have your questions at that time so that I can answer all of them. In project number 2, we're gonna build the converter again, but then we're also gonna learn how to do transfer functions in MATLAB using this. I thought whatever the session I did with you guys was pretty much simple because we did the buck, and all what you needed to do here is you needed to change the places for the MOSFET, the inductance, and the diode in your MATLAB simulation that we did in class, and you should have got it. Again, if you have problems with so we're going to discuss that in details. Once you do the simulation, you're going to plug in the numbers that you already calculated for, and you are supposed to do those basically numbers C and D here in the report. So let's also go through that. So the simulation results in this solution was basically done in PSpice, but it's exactly the same thing. So you're going to create a schematic This schematic will have your input voltage, your inductance value and capacitor value do not change. They are one value that you're gonna choose and you have to stay with them all the time. Then I told you to use for the PSpice, those S break and D break, which is basically your ideal switch and ideal diode in MATLAB. So I wanted you to use simple models so that it doesn't confuse you. And then we put the parameters and the values in there. Once you run it, you need to run it for 4 cases. So you see here, you need to show me those 4 cases. So case number 1, when it's VG min, P out min, which means I'm changing. The 2 things that I'm changing in the simulation, actually 3 things to be fair, that you're changing in each simulation is your VG, your duty cycle that corresponds to that, your RL that corresponds to this, and you run it. And then you do the same thing for the second, third, fourth. So those are the 3 things you change: the voltage, the corresponding power, the corresponding duty cycle that you calculated for this combination. And you have 4 combinations. And you were supposed to show us 2 waveforms here, your I of L, your V of out. Like if we go back, I asked you to calculate I of L or plot I of L, V out. It told you 4 switching periods. Again, why? Because I wanted it to be clear. So you see this waveform here. I can see what is the average value. I can see what's the max. I can see what's the min. I see a simulation name. I see a legend of x-axis, y of axis. This is how you need to present your curves. This is how you need to show that you understand. And if you're not able to do that with the software, it was okay for you to also write it on top of it, either by hand or by paint or whatever, just to show the numbers of it on and off of the values. Again, you're going to repeat it for different cases. All what you change in your simulation is you are changing your the duty cycle, the input voltage, and the output power, which is your load. And then what do you have here? 4 switching cycles. How do you define that? Look at the 0 point here. So again, 1 switching cycle is from here until you go to 0 again. It repeats again. It repeats again. It repeats again. So that's 4. And then I'm zooming to show that on each one of them. So this one, those 4 ones, again, this is just to make it look nice. You can actually show the values of it. If you did not really put it on the waveforms, you can create a table or something and shows that. Again, we're not taking points of this. Once you put me something or show me that you did something, we gave you points. But I wanted to show you a good example for you to follow and actually use for next projects and also for your other classes, and hopefully when you're graduating also for your work afterwards. So I'm gonna skip this part because you were not required to do the detailed switch model, so this was something that you didn't have. So we're just gonna skip this one here. And then actually after that, that's it. I mean, the only case that you had is you needed 1 more case for your nominal, right? So part D for you was to use these nominal conditions and to plot those 4 graphs. So it's exactly the same thing. You change the voltage, the power, and you do that. Let me go here. This is, sorry, I just moved too much. Okay, so this is the 4 cases you want. IL, V of L together. And then what is IL and V of L? V of L, we know that it's a square wave. So those are the same plots that we used to plot by hand in class. Your V of L changes between like the value that you calculate for the first one, the second interval, and then it repeats. Then what is I of L? I of L is a constant value with the slope that's equal to this V of L. So see that when it's positive, we have a positive slope on I of L. When it's negative, we have a negative slope on I of L. And then that basically is for IL, V of L. Then IC and V out is the same thing. Your output voltage, you're showing me that it's regulated or it's controlled by the duty cycle to 48 volts. And your current is basically I of C here that corresponds to this output voltage, right? So again, what is the I of C? I of C is C dV by dt. So the slope is coming from how your voltage is changing. If the capacitance is negative, then the slope of the voltage is going down. If the capacitive is positive, then the slope of the voltage is going up. And then we're asked for 2 more, which is IDVD and IMVM, which is the MOSFETs and diodes waveforms. So this is how they should look like. Again, you can verify you're getting the right thing or not by having what? The diode voltage, we calculated for it, it's 0, and then it reaches here to 48. So this is what you should have maximum and minimum. Same thing for the MOSFET, but the opposite. It's 0, and then it goes to the max, and then it goes to back 0 and up. So when the duty cycle is in D, then you're basically turning on your MOSFET. When it's D prime, you're turning on your diode. So you can see that they're opposite of each other. When the diode is 0, then the MOSFET is the full voltage, and vice versa. With those, then we actually, what is the last thing? Let's go back here. So this we did C and D. And then your last part is estimating the switch diode and overall losses and the efficiency. So in MATLAB, you need to multiply those two. So you need to use a product and you multiply the two. In PSpice, you actually need to use this moving average function and put it the same way it is. So you have two probes here, I and V, and those two probes multiply by each other, and then you get the average function. So that is what we are showing here. And it shows us that the values we calculated for is closer to the values that you get from your simulations. And that's basically your input value, output power, then the losses on the MOSFET and divides, and you calculate the efficiency. For the simulation case, I got 94.2, which is a little bit higher than what you did for your calculated values. But again, it's in the same range, so it's okay. I saw some people got like weird numbers for efficiencies, minuses and greater than 100. Again, what is your efficiency? It's 100% if all the input power gets reflected into your output power. And then it goes down when you have losses. So you had some losses in the MOSFET, you had some losses in the diode. So those losses will contribute to your efficiency and make it less than 100%. Okay? And then finally, just putting a paragraph here on the summary, just to tell us what was the values that you have and what are they talking about. I'll stop here for a minute. I think this finals the project. I want to see if you guys now have any questions or if this answers all the concerns you had in the project. So any questions? Any questions? Is it clear to everyone?
Yeah, it was pretty concise.
Okay, so again, this basically answers the project question. If you guys still have problems or you don't know why you lost points, then please contact me individually, and I'm gonna be going through one by one. Again, please make sure that you learn from this project for your next two. Now, I think we don't have much time, so